We now know the small signal picture of an amplifier using a 2-port. We have to bias the MOS transistor at the correct operating point and come up with a circuit which in its small signal form, in its incremental form will be the 2-port amplifier. Okay. And throughout these discussions, I will continue to use a MOS transistor whose parameters are given here. Okay, these two together mean that the current factor is 100 microampere per volt square and the threshold voltage will be 1 volt. Okay. So, now I said that a 2-port amplifier using a MOS transistor will have this incremental picture, okay, where this is VGS. By the way, I will assume that all of you understand the meaning of this ground. All of these are connected together. It is very common to show points like this because lots of terminals will be connected to this common point and the schematic diagram will look very messy if we draw lines connecting everything. So, just to keep the diagram neat, this is shown. This means that this is connected to this and the load is connected to this and so on. Okay. This is of course the gate, drain and the source, and this is the MOS in saturation region. Okay. Now, this is very simple, nothing much here. All of this Vs appears as VGS and the output voltage across the load RL is minus GMRL times Vs. This is the gain. For the sake of illustration, let us assume that this input source has an Rs which is 100 kilo ohm and the load RL is also 100 kilo ohm. Now, let us also say that the gain magnitude we require is 20 and because the gain of this circuit is negative, the gain will be minus 20 and it will be equal to minus GMRL, and from this we can compute the desired value of GM. GM will be minus 20 divided by minus 100 kilo ohms, which gives you 200 micro Siemens. Okay. Now, we know that the GM of a MOS transistor in saturation is given by mu1 C aux W by L VGS minus VT. Putting these two together, we see that we have to bias the transistor with a VGS minus VT of 2 volts, because this part is 100 microampere per volt square. If this is 2 volts, you will get a GM of 200 micro Siemens. And we know that VT is 1 volt. So, VGS has to be 3 volts. Also, it is useful to know what current is flowing in the MOS transistor. We have to use the saturation region current equation because that is where we will be operating. Okay. And if you substitute VGS minus VT equal to 2 volt and this current factor to be 100 microampere per volt square, you will get 200 microamperes. So, these two give you the operating point of the MOS transistor. VGS has to be 3 volts and ID has to be 200 microamperes. So, now let us see how to get the operating point in the MOS transistor. Okay. This is the MOS transistor whose threshold voltage is 1 volt and whose current factor is 100 microampere per volt square. Now, we saw that we had to have a VGS of 3 volts and VDS, I am showing a voltage source here. I will call it VDS 0, the VDS at the operating point. what should that be? We know that the transistor has to be in saturation. So, VDS 0 has to be greater than or equal to VGS minus VT, and this number is 2 volts. So, whatever this is, this has to be greater than 2 volts. And let me assume, just for the sake of illustration, that this is 3 volts also. Okay. This is an example. It can be anything more than 2 volts. We will take 3 volts. Okay. So, this sets the operating point correctly. Okay. So, we will have 200 microamperes flowing through the MOS transistor if we set up this circuit, but this is not the circuit we want. What is the circuit we want? The circuit we want is such that its incremental equivalent, its small signal equivalent should be like that. Okay. Okay. So, that means that we have to connect the input and the load to the circuit appropriately. Okay. Now, this is when circuits start becoming apparently more complex and difficult. There is no difficulty here. The point is there are many ways to do these things. Okay. We have to set up a certain operating point for the transistor, and we have to make sure that the overall circuit conforms to some small signal picture, that is, it performs some function. There are many ways of setting the operating points and many ways of getting the function. So, the number of circuits that you see, this I alluded to in the introductory lecture also, is very large. Okay, because you can take a whole bunch of operating point setups, whole bunch of functionalities and combine them together. So, the important thing is to understand the logic behind each of these things. Okay. So, now let us go port by port. This is the VGS of the transistor. For the operating point, we need this to be 3 volts, and in the incremental picture, we need it to be Vs, that is, the source has to be connected. Okay. So, if I sum these two, then 3 volts will be the operating point when the incremental source is 0, and when the incremental source is applied, then Vs will appear as the increment across VGS. So, somehow I have to make VGS to be equal to this. Okay. And that does not appear to be very difficult, because I have a voltage source to get 3 volts and I have another voltage source for Vs. Of course, this Vs always comes with this Rs, but adding 2 voltage sources is easy in principle. All we have to do is put them in series. So, what do we do? I have 3 volts and I have Vs and Rs, which is 100 kilo ohms in series. Now, if I connect it to the gate of the transistor and the source is grounded, it is very clear what appears here as the gate source voltage. This will be equal to 3 volts when Vs is 0, when the signal is 0. This is exactly what we want. When the signal is 0 is when we have the operating point. And if you look at the incremental picture, this 3 volt goes away, right. We will be considering only the increments. This Vs will be the increment. Okay. So, I hope you are all convinced that this gives you an operating point VGS of 3 volts, and incrementally it resembles the bottom picture on the input side. Okay. Because this 3 volt is fixed. So, its increment is 0. So, it becomes a short circuit. You will have Vs and Rs between the gate and source. Okay. And if you are not completely convinced, you can simply evaluate VGS. No current is flowing into it. You can see that the voltage that appears here is simply 3 volts plus Vs. Okay. So, this arrangement provides an operating point of 3 volts and an increment of Vs between VGS. So, that part is okay. Now, what do we do for the other side, the second port or the drain side? Remember, what we need is 3 volts or some voltage VDS 0 across drain and source in the operating point, so that it remains in saturation. And also in the incremental picture, we need to have RL between drain and source. Okay. So, how do we do this? Now, you can consider many ways of doing it. Usually, when I ask students to do this, they suggest putting RL between here and there and so on. Clearly, that won't work. Okay, let me show that particular alternative. If I have 3 volts here and I also connect RL here, what happens in the incremental picture? This is the operating point voltage. In the incremental picture, this is a short. I hope you understand why it is a short, because this source is not incremented. Okay, this is a fixed source. This is a 3 volt source. It is not incremented, so it will be a short. So, in the incremental picture, what we get will be, instead of RL, RL will also be there, but it is not relevant, because we will have a short between drain and source. Okay. So, the incremental current source from this simply goes into the short circuit and there will be no voltage at all across RL. Okay. So, this is not useful. So, with a little bit of reasoning, you can see that the correct way to do this is the following. Should have your voltage source that you originally had, okay, and in the incremental picture this point will be grounded, and we want the resistor RL between the drain and ground, which is this, which is also this in the incremental picture. So, what do? We just connect this RL in series. Okay. So, again I hope it is clear what happens. In the incremental picture, this 3 volts becomes ground and this RL appears between drain and ground. So, this is topologically correct. Okay. That is, if you look at the incremental picture, we will have, I am showing the MOSFET here, it is quite common to do this. What is understood is that if this is the incremental picture, you have to replace the MOS transistor with its incremental equivalent circuit, which is the GM and GDS and so on, whatever is in the MOS transistor. Okay. For convenience, many times you do not show the 2-port picture, but you simply show a MOSFET. But if it is the incremental picture, it should be the incremental equivalent of the MOSFET. Okay. So, this is what happens in the incremental picture. Okay. Now, this still has a problem. Remember, what was the current flowing here? It was, let me call it ID naught, the operating point current, that is 200 microamperes. So, if I do connect it in series with RL like this, I will have ID naught times RL, okay, and RL is 100 kilo ohms. Okay. So, ID naught times RL will be 20 volts, right. It appears like a very large voltage and it is for present day integrated circuits, but do not worry about it. Right now, we are just looking at basic principles of amplifiers. Now, clearly there is some inconsistency here. If you apply 3 volts here, you are not going to get 3 volts here. You will get 3 volt minus the drop across RL. And you can consider this circuit and see that if you do actually make a circuit like this transistor will get pushed into the triode region. Okay. Originally this voltage source was directly across the drain and source. So, this is equal to whatever VDS you need. Now, this voltage should not be 3 volts, but it is equal to whatever VDS you need plus whatever drop you have across the load resistor. Okay. So, if you have a 20 volt drop across the load resistor and you want 3 volts here, this should be equal to 23 volts. Okay. So, finally, the picture of our basic amplifier looks like this. We have the input source, and that is connected in series with a voltage source which provides the operating point for the gate source voltage, and we connect it to the gate source of the MOS transistor. On the other side, you connect RL in series with the drain and to provide the correct operating point voltage VDS, okay, whatever that is, let us call it VDS 0, then this voltage will have to be equal to VDS 0 plus the operating point drain current. The operating point drain current also flows through RL. So, operating point drain current ID 0 times RL. So, what happens in the operating point case? I will show that in blue. In the operating point case, this Vs will be 0 and VGS will be VGS 0 and VDS will be VDS 0, and there will be a voltage drop ID 0 RL across this. And in the incremental picture, which I will show in red, the increment, there is only one incremental source here, which is Vs. So, this will be Vs, this will be 0, which means it becomes a short circuit, and this is also a 0, it becomes a short circuit. So, the incremental picture reduces to what we want. And again, I will show the MOS transistor here. It means that for incremental calculations, you have to substitute the small signal or incremental equivalent of the MOS transistor. Okay. Okay. So, this is our basic amplifier. It works, but it has a lot of issues which we will deal with in the coming lessons. Okay. But please convince yourselves that the logical arguments leading to this amplifier are correct. As I said, these logical arguments combining different circuits are extremely important, and that is how you can understand different circuits and also come up with circuits on your own. Okay. Please understand all of those things carefully.